Hello students, so today's class will start off with thermodynamics, right? So it's a very important topic even in our exam point of view, right? So you'll have more weightage for this particular topic as well, and it is a very important topic also, right? So thermodynamics is basically that branch of physics where we study about the conversion of heat energy to other forms of energy, be it let's say work, mechanical work, or any other form of energy, internal energy, right? So whatever heat that you are supplying to a system, how is that system utilizing that energy? So that is what we'll be studying in thermodynamics. Is it utilizing that energy to do work on something? Is it utilizing that energy to increase its own internal energy, or is that energy getting transferred to some other form, right? So we'll be studying about what happens to the energy we give to a particular matter. So whether it is solid, liquid, or gas, so how does that matter utilize the energy that we are supplying? Clear? How is it utilizing the heat that we are giving to it? So that is what we'll be studying in thermodynamics. Clear? So to start off with, we'll be using this term quite frequently, system, right? So system basically means whatever that we are studying, right? Even in NLM, whatever we call as system is that part of matter which is basically under study, right? Which we are studying, correct? Whose behavior we are observing. So in the same manner, even here, system or a thermodynamic system is what we generally call it, or just system. Here, system is something which we can define like this: uh, an amount of matter, an amount of matter whose behavior whose behavior is studied studied due to changes in the thermodynamic variables. Thermodynamic variables. So what are the thermodynamic variables? Pressure, right? Volume, temperature. You can also say density. So these are all different thermodynamic variables. So when we are changing these thermodynamic variables, how is a particular group of matter or amount of matter, so whatever you are basically considering to be studied, so how is that reacting to the changes in pressure, volume, and temperature? So these pressure, volume, and temperature are basically called as thermodynamic variables. So whenever we are studying a particular amount of material and its behavior to the changes in pressure, volume, and temperature, so that material is what we call as a system. So whatever is being studied, right? And anything which is not our system, anything which is outside our system, is basically called as surroundings. So surroundings is basically anything outside our system. So here we'll be in thermodynamics we'll be discussing about the reaction between a system and the surrounding. How do they react with each other? How do they exchange energies between each other? Clear? When I give energy to a system, how much of that energy is the system utilizing? How much of that energy is given into the surroundings? Clear? So that's why we need to study about. We need to know about what a system means and what a surrounding means. So whatever we are observing the behavior of is what we call as the system, and anything which is outside, surroundings. Here, okay. So as I told you, we basically talk about what happens to the energy, especially heat energy that we are giving to a particular system. How is it utilizing that energy? See, we have already discussed earlier in calorimetry that whenever you give energy, heat to a solid, so it can utilize that energy in two ways. One is to increase its own temperature. Whenever you need to increase the temperature, it means you need to increase the internal energy. You know that internal energy of a substance directly proportional to its temperature, yes or no? So the energy which you are giving to a solid, let's say, that solid can utilize that energy to increase its own internal energy, which means increase its temperature, or it can use that energy to change its phase. Correct? These are two ways in which a solid can utilize the energy given to it. Similarly, a liquid can also use that energy to increase its temperature as well as convert into the next higher phase, is into gas. Correct? So those are the two ways in which liquid can utilize the energy. Now what about a gas? So gases, there is no higher form of phase which gas can get into, right? So whenever I give energy to a gas, it can use that energy to increase its own internal energy, right? Can now vibrate with larger amplitudes. The molecules can vibrate with larger amplitudes, thereby increasing its own kinetic energy, thereby the temperature. So that is one way gas can utilize the energy given to it. There is also another way, and a very very important way in which a gas can utilize the energy supplied to it, which solids and liquids don't do mostly here, and that is basically work done on the surroundings. So gases can do work on the surroundings. The reason being, gases can expand. Yes or no? Unlike solids and liquids, even though the expansion is present, the thermal expansion coefficients which we talked about earlier, they are very very small. So even when you supply heat, the size of that won't increase considerably. Yes or no? Whereas gases, I can change the volume of gases to even double, triple, or even 10 times their initial volume. So gases have that ability to expand to higher volumes. So no, when compared to their initial volume. So because of that, what we can say is, if a gas is expanding, so the idea here is that if it has to, let's say, initially if it is in a particular amount of space, if let's say the gas is present in this much amount of space, now I have supplied energy to it, heat to it, and now the gas is expanding like this. Let's say from this position or from this volume, the gas has expanded to this much volume, which means it is now occupying a larger volume. So no. So during this process, what happens is that as the gas is trying to go into larger volume, it tries to push everything surrounding it away from it. So only then it can occupy larger volume. So from this much volume, it is going to this much volume. Whatever was present here initially was pushed away. You understand that the gas is applying a force on its surroundings, pushing it away and expanding into that space. I hope you get what I'm trying to say here. Uh, it is like, for example, let's say you are buying a new piece of land. You have built your house in a particular area, and if you want to expand, if you have to build a bigger house, what will you do? You'll just buy the area which is around your house. So for that, you'll have to spend some energy, or you'll have to spend some money. In a usual scenario, you spend some money and occupy a larger area. You buy a larger area around you. Yes or no? In the same manner, what gas does is, whatever heat you are giving to the gas, it uses that energy and it does work on its surroundings, pushing the surroundings away, and it expands into that region. So to expand into that region, it has to do some work on the surroundings. It has to push that surroundings away. Hope you are getting what I am saying. So just like the example which I told you earlier, if you have to build a larger house, you have to buy the area around your house. For that you need to spend money. In the same manner, for the gas to expand to a larger volume, it has to create space around it. It has to push everything away from it so that it can expand to that region. So to expand to that region, it needs to spend some energy. Yes or no? It does work on the surroundings, it pushes the surroundings away and then expands into that volume. So whenever, please keep in mind, whenever a gas is expanding, so this is one thing which you'll have to keep in mind all the time, gases can expand, and whenever they expand, they are spending energy. They are utilizing some of their energy to push the surroundings away. So whenever you need to, let's say, push something away from you, you'll apply a force and there will be a displacement. And when force and displacement are present, there is some work being done. So what happens here is, whenever you look at a gas which is expanding, means that gas is utilizing some of the energy which it has to do work on the surroundings. Doing work means transferring energy, you know that, right? Whenever someone does positive work, let me write it here, doing positive work, this basically means giving energy, yes or no? So for the gas to expand into its surroundings, it has to do some positive work on the surroundings. It has to apply a force and push it away in the direction of force, right? So let's say gas is initially in this volume and now it has expanded to this volume. So from this initial volume, it has expanded to this higher volume. So what that means is whatever was present here initially, some atmosphere or whatever, so that was pushed away, so it has occupied all of this volume, yes or no? And in this process of expansion, it is pushing everything away. So if there was a molecule of atmosphere somewhere over here, so this was being applied by a force like this and it was pushed away. So that is the reason the gas was able to expand to this volume, right? So it is spending some energy in that process, and that is what we call as doing work. So this is a feature which will happen in the case of gases. We don't discuss about this in the case of solids, because even though solids and even liquids expand, the expansion won't be that much. So if this much amount of a solid, maybe after you increase its temperature, might expand to a slightly larger value. No, but it won't expand to larger volumes. Yes or no? So the work done by solids or liquids on their surroundings will be almost negligible. You don't have to consider that energy. But when it comes to gases, because gases can expand to larger volumes, it can do a large amount of work on their surroundings, that process. Clear? So in this chapter, mostly thermodynamics, although we can study about solids and liquids also, we mostly deal with gases itself, how gases react to the energy given to them, how do they utilize that energy. So will it utilize the energy to increase its own temperature, or will it do work on the surroundings? Clear? So these are all the concepts that we'll be studying in thermodynamics. Clear? Okay then. So before we start off, there are few concepts that will, few terms that you'll have to know here, which we'll be using in this particular chapter, right? Okay, students. Now we'll see this zeroth law of thermodynamics. So it is a very simple law which basically states that if A and B are in thermal equilibrium and B and C are also in thermal equilibrium, then we can say that A and C will be in thermal equilibrium as well. Clear? Thermal equilibrium basically means two systems which are in contact with each other basically do not exchange heat between them. And the reason why they do not exchange heat is because their temperatures are equal, right? If A and B have same temperature and there is no heat exchange between them, B and C have same temperature, no heat exchange between, then there won't be any heat exchange happening between A and C as well. Clear? So yeah, that is what we call as zeroth law of thermodynamics. Zeroth, the one before first, right? So zeroth law of thermodynamics. Now, moving on, the next one is the first law of thermodynamics, and probably the most important law that we'll be discussing. So whole chapter will be based on this idea, first law of thermodynamics. Okay, so first law of thermodynamics basically states that whenever we have, generally let me explain that for a gas. So what it states is that whenever heat is supplied to a particular system, be it solid, liquid or gas, so what happens to that energy? So how is the system utilizing that energy? So it basically, we can state it in this manner: the heat supplied to a system, supplied a system is utilized by it to increase its internal energy, as well as to do work on the surroundings. on the surroundings. Yeah, this statement is what we call as the first law of thermodynamics, and you can write the expression for this in this manner. So if I represent all the heat supplied and change in internal energy and work done in differential form, small amounts, I can write it like this: dq. If dq is the amount of heat that is given to a gas, or could even be a solid and liquid as well, but as I told you, we'll be mostly dealing with gases itself in this particular topic here, because the work done, which I have told you earlier, will be negligible in terms of solids and liquids. So we'll be mostly dealing with gases itself. So the amount of heat that we have given to a system will be equal to the increase in internal energy of the system and the work done by the system on the surroundings. Clear? So the gas will be utilizing that energy in these two forms. One is to increase its own energy, and the other one is to do work on the surroundings. So that is what we call as first law of thermodynamics. Here and here we'll be using some sign convention as well to understand whether heat is supplied or heat is taken, and this is the sign convention that we should be sticking to in this particular topic. We'll have something which is different to this in your chemistry. You'll be studying a different sign convention in chemistry, but as far as physics is concerned, you should be sticking to the sign convention that I'll be going to discuss now. So heat supplied. So whenever you are supplying heat to a gas, so we consider the sign of heat, or dq or delta q, as positive, and similarly heat removed from a system, heat removed from a gas, will be considered as negative. Yeah, so if you are giving heat, so the gas has that energy to utilize, so it has some positive energy to utilize, right? So heat supplied is considered as positive, so it now can utilize that positive energy. Yes or no? So similarly, when it comes to work done, work done by gas is considered positive, and work done on gas, work done on gas, considered negative. So this is the sign convention that we should be using. So what this basically means is, see, think of this heat as some money which you are going to spend, right? So for example, let's say your parents have given you some 100 rupees, right? So they have given you some 100 rupees. So whatever you have, you are taking, the heat that you are taking and the money you are taking, you can consider that as the positive value, right? You have plus 100 amount of money that you can utilize now. Yes. So what you are doing with that 100 rupees? So let's say out of that 100 rupees, you are keeping 50 rupees, or let's say 60 rupees with you. So whatever money that you have has increased by 60, and the remaining 40 is being used, the remaining plus 40 amount of money that you have is being utilized. Let's say you are spending it on someone else, let's say your friends or whatever, you are giving it to someone else, right? So out of the plus 100 you have taken, you are keeping plus 60 with you. So your money has increased by 60, and you are spending some plus 40 amount of that money on someone else, right? On your friends, let's say. So you can think of it like this. So even the gas, whatever heat you are giving to the gas, it can utilize that energy, right? So that is positive energy. Clear? So heat supplied is positive. Clear? Similarly, out of that energy, it utilizes some energy to increase its own internal energy. So whatever increase in internal energy is happening, that is positive, and the remaining positive heat that it has, positive energy that it has, can be utilized to do work, which means giving some energy to the surroundings. Clear? So whenever it gives energy to the surroundings, it means it is doing positive work. You know that already, right? So giving energy to the surroundings means doing positive work. Yeah, so think of it like that, so that you will not get confused with the sign convention. So you take some heat, positive, you give some energy, positive, and you increase your own energy, positive. So by taking heat, you increase your own energy and you give some energy. So all these are positive values. Clear? So yeah, that is how we should be using the sign conventions. Clear, students? And let us see some more applications here. Okay students, now let us discuss about this thing called as state of a gas. Here, so whenever we use the term state of a gas, so it basically refers to the set of conditions that the gas is present in. Here, and what are the conditions that we define for a gas? Pressure, volume and temperature, right? So this set of values of a particular system, so which are also what we call as thermodynamic variables, a particular set of values correspond to a particular state. Okay, so for example, let's say we have a pressure of 1 atmosphere, a temperature of 273 Kelvin and a volume of 1 liter. So that combination is what we call as one state. Okay? And from there, let's say the gas changes its state, let's say from 1 atmosphere, 1 liter, 273 Kelvin. So from this set of values, so let's say the gas is finally reaching some other state where the pressure is 2.5 atmosphere, the volume is, let's say, some 0.5 liters and some other temperature. Clear? So as it goes from this state to this state, it passes through many intermediate states, right? So the collection of all those intermediate states and that whole process, I mean that whole collection of different states is what we call as a thermodynamic process. Clear? The thermodynamic process means the path or the different intermediate states through which the gas passes through as it goes from some initial state to a final state. So if this is the initial state and this is the final state, so as it goes from this state to this state, as it is changing its thermodynamic variables from these values to these values, it will also pass through some other intermediate states as well, somewhere where the pressure is 2 atmosphere, somewhere where the volume is, let's say, some 0.75 liters. It can't suddenly go from this to this, it has to gradually happen, right? So it goes through all intermediate states as well. So the collection of all those is what we generally call as a thermodynamic process. And there are infinite number of thermodynamic processes that a gas can undergo, right? But mostly we will be dealing with some basic thermodynamic processes, some standard thermodynamic processes, so which are what we call as isobaric process. These are some standard ones. There are many other thermodynamic processes as well. There are infinite number of ways in which gas can go from one state to another. We are just discussing a few standard thermodynamic processes, one of which is isobaric process, isochoric process, then we'll have isothermal process, and finally adiabatic process. Okay students, so these are some standard processes that we come across, and you all know that isobaric process is where we have a constant pressure. So we maintain a constant pressure and we change the volume and temperature of the gas. So that is what we call as isobaric process. In isochoric process, we can say that the volume will remain same, or you can say the density of the gas will remain the same, right? So constant volume, you can say. Isothermal process is where you can say the gas has a constant temperature, right, and the other parameters can change. And adiabatic process is that process where you can say that there is no exchange of heat with the surroundings. We'll learn about each process one by one in a while, but I'm just stating what are the basic standard processes that we have. Now before we study about these processes, we'll also have to know about one very important expression as well here, which is basically the work done by a gas. So I've told you earlier that whenever gas is doing work, it is giving energy to the surroundings. If it is doing positive work, it is giving energy to the surroundings, right? How do we calculate that work done? So to calculate that, we can use a very simple idea here. So let's say we have a container like this, in which we have a piston, and the gas which is present inside is enclosed at a pressure of P. So let's say the pressure is P, the cross section area of the cylinder is A, and so the gas which is present here will be applying a force on that piston because the pressure of the gas is P and the area of the piston is A. So you can say that P into A, the force applied by the gas. And now let's say because of that pressure this piston expands, or this piston moves, and the gas expands till here. So this is the final position of the piston. Let's say that the piston the piston moves by a distance of dx. It basically means that the gas has expanded, right? Its volume has increased, and you all know that whenever gas expands, it does positive work. Why? Because it is applying a force on the piston in this direction, and the piston is also moving in the same direction. When force and displacement are in the same direction, means that work done is positive, or energy is being supplied, right? The gas is giving energy to the surroundings, you can say. So it is clearing the surroundings, it is pushing away whatever matter that was present here. So it is pushing it away and it is expanding into that volume. So as I told you earlier, it is just like it is buying this property. I've told you I am buying the land around my house to increase the size of my house, right? So this is exactly, gas is also doing exactly the same. It is buying this volume, clear, by giving some energy, is doing some work, which can be represented like this. The amount of work done by the gas, dW, can be written as the force into displacement, right? The force that is being applied here is pressure, the gas to A, that is the force being applied. I am taking a very small displacement, so the pressure won't change much. Otherwise, as the volume changes, pressure also can change, right? But what I am writing here is for a very small displacement, so you can assume that the pressure is not going to change in that small displacement. So PA will be the force into dx. Now when I integrate this expression, as the gas expands from some initial volume to final volume, you can find the total work done by the gas. So the final expression for work done by the gas, work done by gas, is equal to integral of P into this AdX is nothing but dV, right? So a very important expression this is. Work done by a gas is equal to P dV, integral P dV. Clear? So if pressure is constant in any particular process, so let's say gas is going from one state to another state in a process where the pressure is constant, let's say. So in such a case, you can bring this P outside the integral and you can integrate that, right? If pressure is not constant, so only in the first case, only in the isobaric case, you can bring the pressure outside, integrate that expression and find out what is work done. In all the other processes, you can't bring the pressure outside the integral because pressure will not be constant, it will be changing, right? So you'll have to integrate this expression as it is. Clear, students? So we'll see that one by one. So we'll study about each and every process one by one, and we'll also find out what is work done by the gas in each of these four processes. Clear? So yeah, that is the expression which we should use for any general process. Clear? Whether it is one of these four or any other random process given to you, the general expression for work done by a gas is integral of PdV from initial volume V1 final volume V2. Clear? And also please keep in mind, whenever gas expands, if gas expands, then work done is positive. Yes or no? In this expression, P is anyways a positive quantity, dV will be positive if it expands, and if it expands, work done is positive, and if the gas contracts, then work done is negative. So this is a very important concept that you'll have to keep in mind. Clear? Okay then, so while discussing about these four processes, right, apart from calculating work done, we'll also be talking about one more very important parameter, which call as molar specific heat, molar or molar heat capacity, molar heat capacity. Just like we have specific heat capacity, is amount of heat that should be supplied for a unit mass of a substance. to increase its temperature by 1 degree Celsius. Molar heat capacity, which is generally denoted with C, represents the amount of heat that should be applied to increase the temperature of 1 mole of a substance by 1 degree Celsius. Clear? So if you have to increase the temperature of 1 mole, then how much heat should be supplied is what we call as molar heat capacity. So we can define the value of C as dq by n dt. Clear? When the value of n 1 and the value of dt is also 1, whatever is the value of q that you are supplying is the value of, just like we have ms delta t, here we have nc delta t. Here, so we can also write this as delta q is equal to, if c is constant, right, in such cases we can directly write delta q is equal to nc delta t. So this is a general expression for, so whenever we are dealing with solids or liquids, generally we measure solids or liquids amount in their mass, in terms of their mass, right? So when we are measuring them in terms of their mass, it is better to use specific heat capacity, because specific heat capacity is defined for a unit mass. So there we use delta Q is equal to ms delta T when dealing with solids and liquids. But when it comes to gases, gases are usually measured, their amount is generally measured in moles, right? So it is better to use nc delta T for the heat supplied to the gas. Clear, students? A very important expression this is, and this is a general expression as well for any process that the gas undergoes, whichever process that the gas undergoes, one of these four or any random process out of the infinite possible processes, whichever process the gas undergoes, the heat supplied to the gas in that process can be written as N into molar heat capacity of the gas associated with that process into delta T. So this C value can be different for different processes. So what that means is, see, this kind of behavior happens only in the case of gases, because for a solid, let's say, for a solid, there is nothing like a process, right? What I mean to say is, in the case of a solid, we always have a specific value for specific heat capacity. For example, let's say if I have water has 1 calorie per gram per degree Celsius. So if I have to increase the temperature of water by 1 degree Celsius, right, I have to give 1 calorie of heat for 1 gram of water, right? That is what it means. But for a gas, it is not like that. For a gas, depending on how we are giving the heat, are we giving the heat by maintaining the pressure, or are we giving the heat by maintaining the volume, or are we giving the heat by maintaining the temperature? So depending on which type of process that the gas is undergoing, it defines how much heat should be supplied to the gas. In some cases, in some processes, we might need to give more heat to increase its temperature by 1 degree Celsius. In some processes, we might need to give less heat, clear, to increase the temperature by the same 1 degree Celsius. So gases behave differently in different processes, clear. So the idea is pretty simple. See, think logically. For example, let's say we have a gas which is connected with a piston which can move, free to move, and we have another gas, same amount of gas in the similar amount of container, but this time the container's piston is fixed, and in both cases you are giving heat to the gas. Here, let's say you have given 100 joules of heat here and you have given 100 joules of heat here. Now what happens to the gas? What does the gas do with this heat? So apply thermodynamics first law. The gas can utilize this heat in two ways, yes or no? One is to increase its internal energy, two is to do work on the surroundings. Now when it comes to this gas, which is present in a container whose piston can move, now as soon as I give the energy to this or heat to that gas, the gas will have a tendency to expand, and as a result of which it takes that 100 joules and it tries to expand, right? Because as the temperature increases, the gases will have a tendency to expand. So it takes that 100 joules of energy and it expands. And you know that whenever expansion happens, it is giving some energy to the surroundings, because if it has to expand, it has to occupy some more volume. To occupy some more volume, it has to push atmosphere away from that position. So to do that, it has to do positive work, which means it has to give energy. So what might happen in this situation is that out of the 100 joules of heat that you have given, maybe 75 joules of heat was utilized by the gas to increase its internal energy, which means to increase its temperature. Maybe the remaining 25 joules of heat was given to the surroundings in terms of, I mean, in the form of mechanical work, the form of force into displacement. Clear? So out of the 100 joules, the gas here is utilizing only 75 joules to increase its temperature, and 25 joules is being utilized to expand into the surroundings. Yes or no? But when it comes to this situation, so in this situation the piston is fixed. Yes or no? The piston is not going to move. And now when I supply heat to the gas in such a scenario, what is going to happen? I am giving the gas 100 joules of heat. So it takes that 100 joules of energy. Now what can it do with that 100 joules of energy? There is no other way for the gas, because it can't expand. Yes or no? It can't do any work on the surroundings. So whatever heat that you are giving to the gas will be completely utilized by the gas to increase its own temperature. There is no other way in which it can utilize the energy, right? So whatever heat that you are giving will be utilized either to increase the internal energy or to do work on the surroundings. Whatever the surrounding, in this case the atmosphere, right? But here, because the piston is fixed, and you know that whenever work has to be done, there has to be an expansion or there has to be an displacement of the piston, right? So in this case that is not possible, which means whatever heat you are giving, 100 joules of heat, all the heat, all the 100 joules will be utilized by the gas to increase its own internal energy, right? So obviously if you compare these two scenarios, case A and case B, if I ask you, in which of these two cases does the gas have more specific heat? Or let's call this as 1 and 2. So let's call this 1 and this as 2. So if I ask you to compare C1 and C2, which is greater? So in which case do I need to give more heat to increase the temperature by 1 degree Celsius? You can think, right? Because in this case some of the energy is being utilized for the surroundings as well. So you have to give more heat here to increase the temperature by the same value. I hope you are getting the difference between these two. So whatever heat that I am giving here, 100 joules, not the complete value is being utilized to increase the energy. For example, if let's say by giving 100 joules here, the temperature has increased by, let's say, some 2 degrees Celsius. Let's say here what will happen? Out from the 100 joules that I have given, because only some part of that is being utilized for increasing the internal energy, maybe the temperature rises by only 1.5 degrees Celsius. Clear? So which means in this case I need to give more heat so that the temperature rise is same in both the cases. Do you understand what I am saying? Clear, students? So here the energy is being utilized for other purposes also. So I need to give more heat to increase the temperature by the same 1 degree Celsius. So in this scenario, we can definitely say C1 will be greater than C2. It is the same gas present in the same container, and just because the piston is movable here and the piston is fixed here, C1 is greater than C2. I need to give more heat here and I need to give less heat here. So no, to increase the temperature by the same 1 degree Celsius. Clear? So that is the idea of molar heat capacity. So molar heat capacity of a gas will depend on the type of process that the gas is undergoing. So here the gas is undergoing isochoric process, because I am fixing the piston, means I am keeping the volume constant. So this is an isochoric process, and here the piston is free to move, which means outside force and inside force will always be the same, and because outside force is always the atmospheric pressure force, which is a constant, the inside force will also be constant. So this process is basically isobaric process. So whenever we have pistons which are free to move, so wherever we have pistons which are free to move, so those will indicate the gas undergoing isobaric process. Clear, students? We'll anyways discuss about that later also. But I want you to get this idea that the value of C, the value of heat that I should supply to increase the temperature by 1 degree Celsius depends on the type of process that the gas undergoes. Clear? So C can be different for the same gas depending on the process that it undergoes. Different processes have different C values. Clear, students? So now what we'll do is, for these 4 standard processes, clear, we'll find out what are the C values, how much heat should be supplied to the gas, clear, and how much work will be done by the gas in all these processes. We'll see them one by one. Clear? Okay, students. So first we'll discuss about isochoric process. So you know that isochoric process is that process where the volume remains constant, right? And we can represent that on a PV graph in this manner. So as the volume, as the pressure is increasing, you can see that the volume of the gas always remains the same. So in this case, keeping the volume constant, we are increasing the pressure, right? So what happens there is that temperature increases, correct? We know that in a constant volume process, P directly proportional to T, because we can say that from PV is equal to nRT. So PV is equal to nRT, ideal gas equation is applicable for all the processes, irrespective of whatever gas we have, whatever process the gas is undergoing. So PV is equal to nRT is applicable for the gas in each and every state, for each and every process. You can apply this every time. Clear? So yeah, so V is constant, means P is directly proportional to T, right? That is what that is how we can define an isochoric process. Now work done, the usual definition for work done is integral of P dV, and by definition we can say that P is not changing in an isochoric process, which means change in volume is 0. So therefore work done will be 0. See, this integral P dV is can also be understood as area under the PV graph, area under P versus V curve. Yes or no? Integral P dV, integral y dx. So integral P dV is the area under PV curve. So the area under this line is 0. If this line was horizontal or something like this, then there would be some area below that line. But here, because it is vertical, because there is no change in volume, you can say that there is no area under the curve, there is no work done. So 0 work will be done in the case of an isochoric process, and that is exactly what we discussed earlier. And in such a process, whatever heat we give will be utilized for increasing the internal energy completely, right? If I apply thermodynamics first law, delta Q is equal to delta U plus work done. Because this is 0, so this value here is 0. We can say heat supplied will also be directly equal to the change in internal energy. Whatever heat you are giving is completely utilized for increasing the temperature of the gas. Clear, students? And you all know that for any gas, if I have to write the expression for change in internal energy, I can write it as, you know that the expression for U is F by 2 nRT. We discussed this in KTG. So we can write U for any gas as F by 2 nRT, where F is the degrees of freedom that the gas has. So even here, delta U, which means change in internal energy, can be written as F by 2 nR delta T. Correct? So that is how we represent the change in internal energy. And you know that by definition, delta Q for any gas, we have seen that earlier from the definition of molar heat capacity, C is delta Q by N delta T. So no. So even here we can write delta Q as NC delta T. So the amount of heat supplied to the gas can be written as N C of the gas in that process, because this is a constant volume process, we give a subscript V to this, defining, which basically means that this is the C value for a constant volume process. So subscript V means constant volume process, clear, into delta T. Clear, students? So this is the expression that I will be getting. So there is no work done, otherwise there will be an extra term here as well. So no, there will be an extra term here also, but because there is no term here, so we just have NCV delta T is equal to F by 2 NR delta T. Clear, students? And when I simplify this, I can cancel out N delta T on both the sides, and I'll get CV is equal to FR by 2. So the molar heat capacity of a gas in a constant volume process will be equal to Fr by 2. And the most important thing you can write, you can say here, is that in a constant volume process, you can write delta Q is equal to delta U is equal to N CV delta T. Yes, students. So that is the idea, and also keep in mind that work done is 0. So these are some points which you'll have to know about isochoric process. So constant volume process, the molar heat capacity will be Fr by 2, which means for monoatomic gas, so CV for monoatomic gas. So the CV values for monoatomic will be much. Mono is 3, right? So 3R by 2. For diatomic gas, it will be 5R by 2, and for triatomic non-linear gas, which has 6 degrees of freedom, will have 6R by 2, which is 3R. These would be the CV values for the different types of gases, right? Please keep that in mind. And moving on to the next process, which is isobaric process. Now in an isobaric process, unlike this situation, we will also have an work done term here, right? Because gas will expand. Isobaric process. So this basically means the the pressure of the gas will remain constant pressure. And if you draw a PV graph, so the reason why I am drawing PV graph for each and every process is because we can understand work done from PV curve. Yes or no? Because work done is integral PDV, and area under that curve will give us the work done. So I can understand work done from PV curve. So let's say this is the initial state and this is the final state, because pressure remains constant throughout, so it should be a horizontal line like this, correct? Starting from, let's say, an initial volume of V1 to final volume of. So that is how we represent an isobaric process. And you know that whenever P is constant, you can say V will be directly proportional to temperature in an isobaric process, correct? So yeah, that is the idea. And let us write the expression for work done here, right? So I told you for each and every process we need to find work done and C value. The work done will be how much? The general formula is integral PDV, but because this is an isobaric process, I can bring the P outside the integral, correct? So if I bring the P outside the integral, you can't do this for all the processes, you can do this only for a constant pressure process, correct, students? So yeah, P into integral dV, and you know that integral dV is nothing but delta V, or V2 minus V1. So work done can be written as P delta V only for an isobaric process. For every other process, it should be integral PDV. Clear? Only because I brought this P outside the integral, I am able to write this expression. I hope this is clear. So don't blindly write P delta V as work done for every other process. It is applicable only for constant pressure process. And now we know that this final expression can also be written as PV2 minus PV1 is nothing but this is final pressure into final volume, which can be written as NR final temperature, correct, minus final initial pressure into initial volume is nothing but NR initial temperature. So this expression can be finally written as NR delta T. Clear, students? So P delta V same as nr delta T. So that would be the expression for work done in an isobaric process. nr delta T, a very important expression. Clear, students? Now let's apply thermodynamics first law for this process. The thermodynamics first law states delta Q, the amount of heat that we should supply to the gas, is equal to change in internal energy of the gas plus work done by the gas. Right? Unlike the earlier scenario where all the heat supplied is completely utilized for internal energy, this case whatever heat you are supplying will be used both to increase the internal energy as well as to do work, right? So in general we write the value of delta Q as n C delta T, C representing the C of that process, and because this is an isobaric process we represent it with Cp, P representing constant pressure. Clear? N Cp delta T is the heat supplied in a constant pressure process. Clear? This will be equal to, once again, see delta U, what you can say here is delta U, you know that Q is basically directly proportional to temperature, yes or no? So in whichever process that we are talking about, whether it is isochoric process or isobaric process, the definition for U is always the same. It is always directly proportional to temperature. So no, this is a standard expression. It doesn't depend on which process the gas is being taken in, right? This is always the formula for internal energy of the gas. So change in internal energy will also always be the same. So even here I can write delta U as F by 2 nr delta T. Clear? Plus we already calculated the expression for work done in isobaric process, which is nr delta T. Clear, students? So this is the expression that we get, and if you observe closely from the earlier calculation that we have done, we know that the value of Fr by 2 is numerically equal to the value of Cv. Yes or no? What I am trying to say is the expression that we write for delta U, because U is directly proportional to temperature, delta U is directly proportional to change in temperature. Yes or no? And this expression will remain the same for any process that the gas undergoes. So whether it is an isochoric process or isobaric process or any other process, U has a fixed expression. So in all cases we can directly write the value of delta U as F by 2 nr delta T, and you all know that Fr by 2 is Cv, numerically the value of Fr by 2 is numerically equal to Cv. So what I can do here is I can write this as n Cp delta T is equal to n Fr by 2 can be written as Cv into delta T plus nr delta T. Clear, students? And now when we simplify this, we can cancel n delta T on either side and we will get Cp is equal to Cv plus, and that is the relation between molar heat capacity in a constant pressure process and molar heat capacity in a constant volume process. Clear, students? So Cp is equal to Cv plus R, right? So you can also understand it like this. For example, let's say I take a monoatomic gas. For a monoatomic gas, right? So you know that the value of Cv for a monoatomic gas is 3R by 2 plus R will give you the value of Cp, which is 5R by 2. Now when you look at these three terms are in the ratio of 5 is equal to 3 plus 2, which means 5 is to 3 is to 2, right? So what that means, see, you know that when I multiply this with n delta T, I'll get the heat. When I multiply this with n delta T, I'll get the heat. When I multiply this with n delta T, I'll get the change in internal energy. When I multiply this with n delta T, I'll get the work done. So whatever values that we have here are the indicators of heat supplied, change in internal energy and work done. So what this means is, for a monoatomic gas undergoing isobaric process, clear, we can say that if I give heat to it, So what the monatomic gas does is, it takes that heat, it divides that heat into 5 parts, clear, and out of that 5 parts, 3 parts will be utilized for increasing its internal energy, which means to increase its own temperature, and 2 parts of that heat supplied will be utilized to do work on the surroundings. Clear, students? So that is how you should understand this expression. So isobaric process, if a monatomic gas is considered, so we get 5 is equal to 3 plus 2 eventually, right? Or 5R by 2 is equal to 3R by 2 plus R. And as I told you, this indicates delta Q, this indicates delta U, and this indicates work done. So because they are in the ratio of 5 is to 3 is to 2, 5 parts of heat supplied will be utilized as 3 parts of increase in internal energy and 2 parts of work done on the surroundings. Clear? So which means if you give 100 joules of heat to a monatomic gas undergoing isobaric process, which means maintaining constant pressure, out of that 100 joules, 60 joules is utilized for increasing the internal energy and 40 joules is utilized for doing work. And you can say the similar thing even in the case of some other gas. You can take a diatomic gas. So how would this result be for a diatomic gas? So in the case of diatomic gas, so CV value for diatomic gas is 5R by 2. 5R by 2 plus R will give us 7R by 2. Right, students? So which means the result we get here is 7 is equal to 5 plus. So what is the diatomic gas doing? Unlike monatomic gas, diatomic gas follows a different ratio. If you give Q amount of heat to a diatomic gas, it divides that into 7 parts and it utilizes 5 parts of that to increase its own internal energy, and it utilizes 2 parts to do work on the surroundings. Clear? So that is how we should understand this particular result. Cp is equal to Cv plus R. Clear, students? So let me ask you a question. I want you to think about this. If Q heat is given, let's say if Q amount of heat is given to monatomic gas and diatomic gas, both the gases are of 1 mole, okay, and I have given Q amount of heat to both the gases. So Q amount of heat to monatomic gas, Q amount of heat to diatomic gas. Whose temperature will rise more? Will monatomic gas's temperature increase more or diatomic gas temperature increase more? So try to think about that. So try to leave some gap after this. So try to think about that and in 2 or 3 lines give the explanation for that. Why would the temperature of one gas increase more than the other when same amount of heat is supplied to both? Which will rise in temperature more and the reason for that? Clear? I want to see that in your notes. I want you to write the logic behind which temperature will rise more. Clear, students? Okay, students, now we'll discuss about isothermal process, right? So PV is constant is how we write the process equation, correct? So temperature will remain constant and PV is equal to constant can be represented on a graph like this, correct? So a hyperbola. And if I have to find work done by the gas in this process, here it will be slightly difficult when compared to the earlier scenarios, because in the first case isochoric work done was 0. Second case we got a straight line, which means area under that was a simple rectangle. Yes or no? Delta V into P. That is how we found work done in isobaric process, right? So in isobaric process the graph was like this, P versus V. So if I have to find the work done, so work done is basically area under the curve, right, which is this area, and because we have a rectangular area there, it is easy to find the area of that rectangle. We also calculated that earlier, which we got as this length is delta V into this length, which is P delta V. We can write work done in isobaric process as P delta V or NR delta T. We have seen that earlier, right? But here, because we have a hyperbola, calculating the area under this slightly difficult when compared to this. We need to integrate, right? Okay, then let's do that. So the expression here is integral of PdV, that is the expression for work done for any general process, right? And because in an isothermal process, PV is equal to, let's say, if I write it as nRT, we know that this whole term is a constant because temperature is constant. This whole term is a constant, correct? So what I'll do is, to evaluate this integral, I'll bring this whole either P dV, because I have two different variables here. I'll bring it into a single variable form so that I'll be able to integrate it, and I can write this as integral of, what I'll do is I'll remove P from here and write it in terms of V, so that I am able to integrate the volume, right? So P can be written as nRT by V, correct? So nRT by V into dV, and you know that nRT is a constant. I can bring that outside the integral, so I can write this as nRT into integral dV by V, and you all know what is integral dV by V? Ln V, correct? So this becomes nRT ln V, and what are the limits I should substitute for V? We can substitute it as, let's say, V1 V2. Yeah, if the gas is expanding from, let's say, this volume to this volume, so this area will be the work done, correct? So volume V1 to V2, so I'll get the expression for work done as nRT ln V2 by V1. Clear, students? So that is the expression. So this will be the expression for work done in an isothermal process. Clear? And you know that in an isothermal process, because the temperature is constant, delta U will be 0, because delta U is, the expression for delta U is always equal to F by 2 nR delta T or NCV delta T. So no, you can write NCV delta T as the value of delta U for any process, because remember, just because I have written CV here doesn't mean that it is applicable only for an isochoric process, right? So what I am doing here basically is, for every process the value is F by 2 nR delta T, and the value of F by 2 R is exactly same as CV. So that's why I am representing it as NCV delta T. That is all. Don't think that because I have written NCV delta T is applicable only for constant volume process. No, this is the general formula, F by 2 nR delta T. I am just writing the value of Fr by 2 as CV. That's it. Clear? So because this is the expression for delta U, which is directly proportional to delta T, but there is no delta T in a constant pressure process, sorry, constant temperature process. This is 0, so this will also be 0, right? So now when I apply thermodynamics first law, which is delta Q is equal to delta U plus W, what I get here is this term will be 0, and we can get delta Q, the heat supplied to the gas in an isothermal process will be completely utilized to do work. None of the heat supplied is utilized for increasing the internal energy. Clear, students? So we can write delta Q is equal to W, and that will be equal to nRT ln final volume by initial volume. You can also write this as nRT ln initial pressure by final pressure. So no, because V final by V initial is same as P initial by P final, because in a constant temperature process, P initial into V initial will be equal to P final into V final. Based on this, I can write Vf by Vi is equal to Pi by Pf also. Clear, students? So heat supplied will be same as work done by the gas. Clear? And that can be written as nRT ln Pi by Pf. Clear? Or Vf by Vi. So that is the expression, and we can also find the C value for this process. And if you remember how we defined the C value, C is defined as delta Q by N delta T. Right? That is how we define the C value. And please remember, for a isothermal process, delta T is 0. There is no change in temperature. Right? So what this means is, C for isothermal process is infinity. Clear? Now, what does that physically mean? So, you know that C basically means heat that should be supplied to increase the temperature by 1 degree Celsius. So, for isothermal process, it is infinity. What that means is, even if you supply infinite amount of heat to the gas, if it is undergoing isothermal process, temperature won't change. Yes or no? So, yeah, that is how we should understand. So, to increase the temperature of a gas by 1 degree Celsius in an isothermal process, which we can't do, we need infinite amount of heat, which is not possible as well. Clear? So, that is what this infinity means here. Clear, students? So, you'll have to definitely remember this nRT ln V2 by V1, and please keep in mind that this NCV delta T can be used for any process for writing the expression for change in internal energy. Clear, students? And now the final process of the standard ones, adiabatic process. So, adiabatic process by definition is that process where the heat exchange with the surroundings is zero. No heat exchange with the surroundings, which means the system is not taking heat from the surrounding nor giving heat to the surroundings. It is not taking nor giving. Clear? So, no heat exchange, no exchange of heat, no exchange of heat with surrounding. Clear, students? And which means delta Q is 0. Now, in this particular scenario, if I have to find out, I have to apply the thermodynamics first law, which is delta Q is equal to delta U plus W. Because this is 0, you can write 0 is equal to delta U plus W, which means W is equal to minus of delta U. Okay? So, work done by a gas in an adiabatic process will be the negative of change in internal energy. Clear, students? We will discuss in detail about adiabatic process in the next class. Clear? So, I will also derive the expression for this work done by using the definition of work done, which is work done is equal to integral PdV. So, we can derive this result using this also. We will do that. Also, we will derive the process equation. Just like we have PV is equal to constant here, we also have a process equation for adiabatic process. So, we will see that derivation in next class, right?